Today, I want to talk about the efficiency of the Victron energy storage systems that we use so much. It's Warwick here from Thanda Solar, and we are a Victron distributor that services clients in Southern Africa. We are, I guess, a specialist Victron distributor. We focus on the details to a very high degree. We assist with a lot of R&D at Victron as well, and lead a couple of projects for them. And we do lots of complex integrations and automations in Victron systems. But today, what I want to talk about is efficiency. If we have a look at what's on the screen here, which is our what we're used to seeing in VRM, what I've done on the installation data on this install is I've chosen the previous month. So I want to have a look at July 2024. And if we have a look at these figures, one of the things that comes up most often is that, as a query from customers, is that the numbers don't add up, okay? So if we know that we have had 589 kilowatt hours of consumption, and we have generated 533 kilowatt hours of solar, then that means that we should have used 56 from the grid, all right? But if we subtract what we used from the grid, then we've got 95 kilowatt hours that have been lost, okay? And if we take that 95 kilowatt hours as a function of the production, then we're looking at a 18% loss. And it's an efficiency loss. It's a round trip efficiency. And what I'd like to talk today about is why that loss exists. So in this particular system, we've got a Quattro 10, which uses the very robust legacy copper toroidal transformer, the low frequency design, which has been so trusted and relied upon in the bush, on marine craft, in RVs, in vehicles, service vehicles, in off-road vehicles. You know, anywhere where you need something that's tough and can take a punch, the Quattros and Multipluses or the Phoenix inverters have been the solution. Only recently, Victron introduced the RS family of products, and soon the HS, the high voltage, high frequency, three-phase products that are on the way. And those have a different, more modern topology where they use high frequency, high voltage switching electronics to transform DC into AC, right? And the conventional wisdom over the years has been that a tough transformer-based solution is more robust in the long run. But you know, Victron has waited, bided its time, and come up with a design that's extremely efficient. So here we're talking about a 17.8% loss. So you know, you would like to see a loss with this new equipment being lower in that respect. A higher quality sine wave out of the system, and similar characteristics in terms of toughness and the ability to take a punch. And what I mean when I say take a punch, I mean startup loads like motors, where the motor is rated as a 10 kilowatts, but it requires 40 kilowatts to get started. Can the inverter provide that instantaneous peak power just to get that motor started before it settles down to its 10 kilowatts? And so the conventional wisdom has always been, and certainly our experience in the field, is that the transformer-based old school stuff can be relied upon for that. But from what we've seen from the multi-RS family and the very early testing of the HS family, they seem to stack up. They seem to be delivering comparable performance with improved efficiency and with improved output power quality. So we're very excited about those. But back to the question here, where did this 95 kilowatt hours of energy go over this particular month? Where was 17.8% of it lost, in inverted commas? Now, something that's worth thinking about is that when you throw wood in a fire to generate energy, to boil some water, for example, you are taking the sun's energy that's been stored in wood and you are converting it into water. Now, the same analogy could go for trees that became coal that fed a power station to produce electricity to boil a kettle, right? What's the energy efficiency of the sun that produced the trees, that produced the coal, that then produced the electricity, that then boiled the water? It's extremely low. It will be, I don't know, way below a fraction of a percent over the many thousands of years that it took for the sun to create the coal. But even if we're talking about burning wood, the many years that the sun casts its energy on the trees, and the trees then convert that into wood, and the wood then gets chopped down and burned, I'm sure you're talking about, again, a fraction of a percent energy efficiency. So when we're talking potentially 80 to 90% energy efficiency in these systems, that's actually a very good thing. Now, what we see very often is someone will pull up the data sheet for one of these products, and they'll see that on the data sheet, the maximum efficiency is 99%. But the important thing, obviously, is the word maximum. The MPPTs, for example, in the installation we're looking at, the MPPTs there are about 95% maximum efficiency, and the MPPTs are about 99% maximum efficiency, and the inverter charger, the Quattro in this case, is about 95% efficient. So what does that work out to? Assuming the power gets to the DC bus at 99% efficiency, and the inverter is inverting it to AC at 95% efficiency, we've got an overall round-trip efficiency maximum theoretical efficiency of 94%, which means in the best case theoretical scenario, we are losing 6% of our power. So in the case of this installation, you can see that with the exception of some power outages between the 17th of July, 16th of July, and 21st of July, 22nd of July, the battery is being kept charged at this site. And for the purposes of this conversation about energy efficiency and round-trip efficiency, that's relevant because if you have to charge a battery and then discharge a battery and recharge it and discharge it, there are charge and discharge efficiencies to take into account. So you can imagine, for example, that it takes 105% of the battery's capacity to get it full, and you only get, say, 95% out of it. Now, with lead acid technology back in the day, that was a real factor. You could lose up to 20% of your battery capacity to charge and discharge losses. With lithium, much, much higher efficiency, sometimes quoted in the 99s, sometimes lower, but the bottom line is it's it's not good. It's much better. So, sorry, I'm watching my 3D printer here, and it's messing up. I should probably stop that. Failed prints. I should probably just leave that in because that's coolness creds, eh? So, and we'll also get to see how good Zoom's background noise cancelling is with that off compared to with it on before. Okay, so the point is that lithium batteries are far more efficient, but there is still a few percentage points likely of losses. The other source of losses is wires, depending on what size your solar cabling is, what size your battery cabling is, what size the AC cabling is through your system. You might, if cables are ever warming up during the process of being used, heavy load, heavy grid feed, and that kind of thing, then they will be they'll be generating more losses, transmission losses, than a cable that was larger, was oversized. And then you also have terminal losses. So if you've got connections that are less tight than they could be, or there's corrosion somewhere between a lug and a busbar surface or something like that, you will have a bit of resistance in the connection that could be, again, introducing some losses. But what's actually most important is if we have a look at one of Victron's internal documents here: output rating, operating temperature, and efficiency. So this is a document that Victron has listed on its website. And if we have a look at section 3 of this document, we see this curve and the table above it that's provided. And in this case, we're looking at a Phoenix inverter 24-3000, okay, the 3 kVA Phoenix inverter. The Phoenix inverter here uses the same toroidal transformer that the Quattro and the Multiplus does. So we can expect similar sorts of numbers out of the other products. And what we see here is that this inverter is maximally efficient, around 94%, at an 800 watt loading. Okay, so a 3 kVA in the Victron world has a crest factor applied of around about 80%, or 0.8, which means that its maximum output power is 2400 watts, okay, on a sustained basis. So if we take that 800 divided by that 24 watts, what we're saying is that the sweet spot for this particular inverter is around about 33% of its rated maximum wattage, power output. So at 33%, this particular inverter is most efficient. Now, at 3 kVA, sorry, at 2.5 kilowatts, which is around about 3 kVA, it's already losing 12% by 11.7% by converting DC to AC, by inverting DC to AC. And when it starts providing burst peak power for short periods of time above the 2.4 kilowatt sustained rating, then the efficiency goes down even further. So at a burst power provided of 5 kilowatts for a motor starting or something like that, that instant that the power is supplied, it's supplied at an even lower efficiency with a loss in excess of 20%. So that's worth noting. And what's important also about this table is where you have sites that are feeding into the grid, they're going to spend more of their time closer to the inverter's rated maximum output power. compared to systems that are throttling their PV because they are unable to feed into the grid. So it follows that where systems are feeding into the grid, you should see this loss number creeping up, potentially towards 20%, between, I would say, 15 and 20%. But where systems are operating completely off-grid, or where they aren't feeding into the grid, and the nominal or average power consumption is much lower, we should see those losses being even less. And I'll try and find a site that's a good example of that for us to have a look at. So if we go back here, we understand this particular site is feeding into the grid. And as we saw there, it had a 17.8% loss. Let's have a look at a multi-RS site. So we said the multi-RS was the high frequency switching technology that's more efficient, generates better output power, and should have fewer losses. So on a sample of one site versus another, which is certainly not representative, but it tells us something, let's have a look at this. So for July, this particular site consumed 1,066 kilowatt hours, and 732 of that came from solar, and seven and 94 kilowatt hours came from the grid, right? Which means that the losses in this case, also a case where the site is feeding power into the grid, albeit less. In this case, the losses are 79.3 kilowatt hours. And if we take that 79.3 as a proportion of all the solar generated, we get 10.8% loss. So this would suggest to us certainly that this multi-RS site is performing better from an efficiency perspective than the Quattro-based site. But as I mentioned, there are other factors in play. The multi-RS site by definition has the PV wired internally, so it isn't going to a separate MPPT down to a bus bar. So there's potential for wiring losses in the Quattro-based system, whereas this one has less potential for that. The one might be operating in a warmer room than the other one. A cooler inverter is definitely a more efficient inverter. So it's an indicative example for you, just so that we can help understand these concepts. But if we did a broader survey of transformer-based sites versus RS-based sites, I think we would find a very clear trend. So let's have a look at a site that's not feeding into the grid. So here we have 889 kilowatt hours. We have 400 kilowatt hours from the grid. Let's factor in the 0.4 of bleed-in, which does happen as the system tries to regulate itself. And we subtract the 562. Right. So then let's have a look at that 72 as a proportion of solar generated. So this site has a 12.9 or a 13% loss, which means it's 87% efficient, which is way better than the 82% that we saw on the site that was feeding into the grid. Keeping in mind that this is also a transformer-based site. This is not a multi-RS site. So the efficiency of this site is approaching the level of a multi-RS that's feeding into the grid, and is 50% better than a similar site that is feeding into the grid. So I hope that has been helpful and has answered some questions. And I'll find out what we're going to chat about next time. Ciao.